I would say stick to that. Hello? Oh, Gordon?
Sorry, I'm late.
Yeah, I was also late in Matt and Curtis.
So yesterday I told him tomorrow we'll start the session.
Yes.
Okay.
Oh yeah, I suggested your name to him. Did you see that message that I wrote on your phone?
Yeah, I got
You did.
I looked at it. I understand.
Yeah.
I think for homework 8, like some of the comments you wrote weren't complete.
What you wrote?
Like you on homework 8, like you wrote like look back at, and then like that was it.
Oh, then
Like
it's.
some of your comments got cut off.
I see. I did not. That was not intentional.
Maybe.
Yeah. Maybe I didn't save it before I. Like after that, you actually save it, and yeah, okay. I don't remember.
Yeah. Do you teach 203B this semester? 203?
203B, no, 203A.
Oh, okay. Okay. I got asked if I could tutor or find somebody that could tutor a 203B student. I was just wondering if you were the teacher.
No, I'm not sure, but you're allowed to, and that's good. What I typically say is that when students come for help, I first refer them to the physics help desk, which is free and there are lots of hours, and graduate students, physics graduate students who are teaching it. And I say stick to physics students because most of the times the notations will help, and so you fit in there perfectly well. So that is a service in a sense, and you should you can charge money. That's perfectly fine. It's good, yeah. Okay. So we have an exam on Friday. Midterm 2. And it's in class. Because he's seeing you, some of you guys, for the first time in the semester in what? In real. A couple of questions that I think you should all look into the current homework. What is this? There will be a question on evaluating the quadruple movement. That also means that you'll have to calculate dipole and monopole moment. So you should, and it is, if you got it wrong in the homework, it is relatively straightforward. Just pick it up. It's an easy place to score. So it's like calculating the center of mass. And I usually ask it for point charges. And maybe that would be another problem in which I might ask continuous charges, but typically I ask it for point charges. Then of course we have legendary polynomials. And mostly it's connection with the moments. That's what. And so there will be more problems, but most importantly, today's lecture there will be a problem. So today's lecture, there will be a problem associated with. I'm going to teach you a method of how we can do electric potential for an arbitrary charge, or not arbitrary, or in principle arbitrary, but I will choose specific charge configurations on a surface of a sphere, and you should be able to do that for arbitrary. I'll do it for certain L's, and you should be able to do that, reproduce that at least for you. So that's for one thing. So with that, let me proceed. So let's refresh legendary polynomials. This is a sort of a summary of what legendary polynomial is. Legendary polynomials are defined using a series. So you start with r minus r prime. In general, this is a complicated expression in theta, theta prime, phi, phi prime, and r prime. But if you choose this on the z-axis, basically setting theta equal to 0. So that simplifies things significantly, and you have, this is 1 over r squared plus r prime squared minus 2 r prime cosine theta prime. And the legendary polynomials are defined as a series. One over r L equal to 0 to infinity r prime over r raised to L, and L cosine of theta prime. And let us, there's a small, it is actually symmetric in r and r prime. So I can swap it whenever it is the opposite, but let's say r prime here is less than r. So the observation point is always greater than all the r prime sitting in. So that's your definition of legendary polynomial, and this is what we did. Taylor expand this and capture the coefficients of these terms, and you identify them as legendary polynomials. In particular, there is a nice formula we saw. So this is PL in terms of x, where x is cosine theta. So this is d by dx L times x squared. And it's also good to point out that this is, if you were to write this in terms of PL cosine theta, which is what we often work with, because we have theta as our variables that we're working with. In that case, this is d by d cosine theta. So treat the whole cosine theta as a single variable, right? Pretend it to be x, right? That is how we want to do that. So this is cosine squared theta minus 1 raised to L divided by 2 raised to L. By any chance, if there is a sine theta there, replace it as cosine theta inside and do the operation. So that's how we define it. And there is one more thing which we did not prove, but which is very useful. We said that legendary polynomials form a complete set, and then it satisfies an orthogonality relation. Orthogonality relation. And that is that if if you were to evaluate the x from -1 to +1, P L of x, P L prime of x is equal to 2 over 2L plus 1 times this is a standard thing that you're going to start using more often as you proceed along. Today we will go slow, but as you go into the semester, it's expected that you get used to this idea very much. So this is a equivalent of the idea that if you write EI to represent, so I is equal to 1, 2, 3, where E1 is equal to I hat, E2 is equal to J hat, and E3 is equal to K hat. So that's your unit vectors. Then it is good to notice that EI dotted with EJ, what will that be equal to? Try again.
Oh, 3.
No. Notice I can take 3 values, J can take 3 values. So it's a tensor, so it's a delta ij, very good, right? So that means that if they are the same, that means it is I dotted with I or J dotted with J or K dotted with K, that's equal to 1. But if they're not the same, it is 0. So that's orthogonality relation, right? This is what is called orthogonality relation, normal vector space. This is exactly the same as this, or conceptually it's exactly the same as this. If you were to think of this as like summation, so remember this sum is on vector variable. So this is, let me write this as L dotted with L prime is equal to delta L prime, right? Where sum is over vector, like over dot product. Like dot product is nothing but a sum, right? The first component of EL, first component of EL prime, second component of EL prime. So that's that dot product. And if they're the same vectors, it's 1. If they're not the same vectors, they're 0. That's the same thing here. That summation gets replaced with X. It has lots of components. X is the components of a vector. If you think of this as a vector, at each point X, the function X variable, are components of that function, if you want to imagine it like that. So it's an infinite dimensional vector. It's called a function space. Instead of a vector space, it's a function space. It's a good thing to have that concept in mind, but it comes with unusual problems, like when you do the sum, it's over a continuous variable, so it need not be convergent. So if you have convergence in hand, this is a one-to-one understanding. It's perfectly fine. But usually convergence is a problem, but not in this well-known functions, it's not. But if you're doing in a new territory, be careful. And this is a vector, that's a vector. So that's the idea of a vector space. Here, there is an orthogonality and there is a completeness. Here also there will be an orthogonality or completeness. Every vector or every function space has this feature. Always you will have a differential equation. So this is called a generating function. Generating function. Generating function, orthogonality, completeness, then there's a differential equation, then the recurrence relation, all that is applicable for any functions. But we will today use only the orthogonality relation. We will want to use this in terms of angle theta. So how does that work? So you substitute x is equal to cosine theta, then dx is equal to minus sine theta d theta. if theta is equal to minus, sorry, x is equal to -1, theta is equal to pi, and when x is equal to +1, theta equal to 0. So it goes from pi to 0, but then this minus sign can be used to switch the limits. So this can be written as 0 to pi sine theta, and PL cosine theta, PL prime cosine theta, and that's equal to 2 over 2 plus 1 delta prime. And we will prefer to use it in terms of angle theta. Any questions on this? This is just a summary of Legendre polynomials. Next, let's construct a problem where we have a charge distribution on the surface of a sphere. So a charge distribution on a sphere, on the surface of a sphere. A sphere of radius a or r. So what are we meaning here? So we have a shell, if you want. So let's say radius r. The radius r, and there is charge up here everywhere on the surface. So there could be more charges here, there could be less charges here, there could be negative charge here. So that's negative. So there could be too many negative charges. So, but it's all on the surface, and there is a distribution there. And if we want to specify that, we need to give an angle. So what is my charge density for this? Charge density, since it's a source, I use r prime. I would like to keep this angular dependence arbitrary, and let me call that angle theta. But so yeah, let me call this sigma theta phi. Times, it's all on the surface of a sphere. So this is delta of r prime minus r. That's my charge density. What are the dimensions of sigma? Of this function sigma? What would be the dimension? Charge per area, because this is charge per unit volume. This is 1 over length, so this is charge per unit area. So this is charge per unit area. If you have equal amount of charge, if it is uniformly distributed, then you can say it is q over 4 pi a squared. But you don't. We are just saying that this is arbitrary sigma, which is provided to us. Right? And we would like to know what is the electric field associated with this distribution. And at this point, it is arbitrary, but we'll specify some specific ones, and you'll see that it's very easy. Any questions at this stage? Right. So that's your charge distribution, and our phi, remember, are the electric potential, using which you can we can actually calculate things on the or we can calculate the electric field, and this is given by 1 over 4 pi epsilon naught, and this is d cube r prime, and we have charge density prime over r minus r prime. Oh, I should actually specify something. Since we are going to use Legendre polynomials, this has this restriction that the observation point has to be on the z-axis. So let's the charge distribution on the surface of a sphere, and let's say this is at z equal to 0. We'll be able to later on take this restriction off when we do spherical harmonics, which are generalization. When you take off this restriction, the new functions will be called the spherical harmonics. But until then, we have to restrict ourselves to z equal to 0. And they are more complicated structures, so we are wait for. So we are not going to keep it very general. We are not calculating the electric potential everywhere, so it's only along the axis that we will calculate. Yes.
So why are we setting z equal to 0 when like are in the z hat direction, then theta equal to 0?
Yes, exactly. And to set theta equal to 0.
Yeah. So I'm just confused by like what z equals 0 means, I guess.
Oh, I didn't mean z equal to 0 on zx, theta equal to 0. Sorry. I meant on the z-axis with theta equal to 0 on z-axis. Yeah, good question. So we are saying on the z-axis with which means theta equal to 0, which leads to the simplification. Notice there is this denominator there. That is where we are going to bring in our legendary function. So let's do this. So we can immediately write this as, so this is equal to 1 over 4 pi epsilon naught. This is spherical coordinates. So this is 0 to infinity r prime squared r prime 0 to pi sine theta prime d theta prime and 0 to 2 pi d phi prime. Right. We are evaluate this integrals, and this is sigma theta prime phi prime. Oh, this was theta prime phi prime, right? I think I put that theta prime phi prime here. And delta of r prime, and the denominator is, since we are on the z-axis, this is r prime or r squared plus r prime squared minus 2 r prime cosine theta prime. Please appreciate the fact that this is not a simple expression unless you do this setting on the z-axis. If it is not on the z-axis, this is cosine of gamma. It involves theta and theta prime. It's a reasonably messy expression, so that integrals are not easy. We can, whenever there is a delta function, the integrals are most immediate. We just have to replace this r prime with capital R. That's our delta function integrals prescription. So evaluate that. So that's equal to. So I'm going to complete the r prime integral. So that brings in r squared over 4 pi epsilon naught. So replace everywhere I see an r prime, replace it with capital R. And forget the integral. 0 to pi sine theta prime d theta prime 0 to 2 pi d phi prime and this is sigma theta prime phi prime over, now this is r prime is capital R, so this is r squared plus capital R squared minus 2 r capital R cosine theta prime. To appreciate the fact that what we are actually doing, let us do one more simplification. Let us say that this is actually sigma of theta prime alone. We do not have any azimuthal dependence. That is just to appreciate the simplicity that's going to happen. And I should say that this is simple in the sense of a new technique. It is a simple thing to do, but these integrals are not simple. We will have to use the properties of Legendre polynomials to. So If this is phi prime independent, then I can proceed and do this integral. This will actually be 2 pi. So, and then I am left with one integral alone. But instead of that integral is not easy to do because I don't know sigma theta prime. But for that, what we will do is we will now put in our, it seems like we're going to complicate our expression because this is a known function and then I'm putting a series in there, but it will lead to simplification. So let me do that. So I'm going to do two things. So if you, yeah, so this is equal to 2 pi from here, 2 pi r square over 4 pi epsilon naught and 0. Let me go to the other board maybe. Yeah, let's do this in 2 steps. That's sine theta d theta prime and sigma theta prime over. Let me do one more thing. I will pull out the 1 over r here. So that's a good thing to do. So let me pull out the. So this is 2 pi r square over r, 1 over 4 pi epsilon naught. Okay, because then that 1 over r structure starts showing up. And this is 1 plus r over r square is 2 times I write it like that because that's how our, because this 1 over r has to show out outside. Okay, so that's good enough. It seems like we are not doing anything. Like we are actually, notice we're not done in single integral as far, at least the relevant integral. We didn't even specify our distribution. So in that sense, this is more of a formal steps rather than actual evaluations. So let me proceed. Okay, so phi electric potential at theta equal to 0. Let me say, so this is r and theta is equal to 0. That's important that we are doing that. And now I put in my legendary function structure in there. So this is 2 pi r square over r 0 to pi sine theta prime sigma theta prime, and I put in all legendary polynomials. Like that was a single integral first. It seems like we are going in the wrong direction in the sense we are complicating it. So it's a sum and an integral now to do. So we undid a closed expression. But there are advantages here. Now replace this integral and the sum. That's a general technique you will always use. So this is 1 over 4 pi epsilon naught. Bring out, you want to isolate the angular dependence completely into an integral. This is 0 to pi sine theta sine d theta prime sigma theta prime and PL sine theta prime. And this is where you want to start using an interpretation here, remember these are unit vectors, right? This is an unknown function. These are unit vectors, so that's a component of this function in this basis. That's the way you want to interpret that, and that can be done for a specific function. And so now from this point on, we have to specify. So let's do an example. So this is where I say that I will ask this in the exam. I am going to do this for a particular sigma, but I will give you another sigma in the exam, and you will have to do that. So let's say sigma of theta prime is equal to some constant sigma. Some constant, right? This is constant. So it's just to not confuse. So let's say beta. So beta times cosine of theta prime. That's it. But if you remember your legendary polynomials, which legendary polynomials gives you a cosine theta prime? From your homework? First one, right? So P0 of cosine theta is equal to 1, P1 of cosine theta is equal to cosine theta, and the next one gives you P2 of cosine theta is equal to 3 by 2 cosine square theta minus half, right? And so on. I think this is a minus, right? Is it a minus or plus? Minus, right? Yeah. So this is nothing but we can at least write it as a fancy way as P1 cosine theta. So this is equal to beta times P1 cosine of theta prime. But that is a good information because this means that this is a vector, right? That's like this is a basis vector, right? So that's crucial. So now let's put this in there. So now notice how simple this gets, except for the interpretation because you guys are new in this. This is 2 pi r squared over r sigma L equal to 0 to infinity. Beta is a constant. I can bring it all the way out here, so I'll keep it somewhere here. So this is beta. And there is r over r raised to L. And this is 0 pi sine theta prime. This time, this is P1 of cosine theta prime, and PL is arbitrary, but is decided by the sum. Okay. Notice that the 1 is the L. And this integral is orthogonality statement. Like it's like saying I and a J came together, then you know that this L will survive only when L is equal to 1. All other components are 0. So this whole integral collapses immediately. This whole thing using orthogonality, is delta 1L. It's a delta of 1L, and it is 2 over 2 times L. L is 1 though, right? So because L is 1 now, plus 1, it is 3. 2 times 1 plus 1. 1 is 3, right? But whole integral is just that. So this becomes beta (2 pi r square. Write that here. Or, and that is the sum. L 0 to infinity r raised to L. And let me place you. So this is like we don't have to replace that L at this point. This could be done like this also. L is 1. I can either do it at this stage or at a later stage. Right? This is delta 1 L. Right? Using orthogonality, this is what you get. What is the sum equal to?
Times 2/3.
2/3. What did you say 2/3?
No, in the second part.
Oh, yeah, this is 2/3. Good. So basically, this whole sum is again doable. You just put L equal to 1. Right? Notice how, like, we have not done anything. It's a new way of doing it, that it is a formal manipulations. We do this integral using orthogonality. This sum we are using because this survives only when L is equal to 1. Out of all these terms, only the first term, or not the first, the L equal to 1 term survives. So I just have to replace L equal to 1. So the next step is using the property of Kronecker delta here. This is 2 pi r squared beta over r. Replace L with 1. That's all I have to do. So replace L with 1. L is 1 now, and 2 times 2, 1 plus 1. And forget the Kronecker delta. So you got the answer. So really all the integrals and summations are done formally. We actually did not use any integrals here, but we used integrals in the sense that we used special function properties which someone else has done it. It's like saying sine theta cosine theta. Whenever you get an integral, you use standard ways of doing that. So this is now a new way of doing it. These are special functions. Legendre functions are known. It's like sine and cosine. Right? If you get this, you can do this. And so the idea is to bring the structure together. Like in this case, I brought it for you. So that's the experience you want to build, that you want to be able to build. Yes.
So for delta, if it was like delta 2L and L was 2,
L is 2.
then okay, that's still
Then you replace L equal to 2.
okay.
Right? If this was, so for example, an immediate question I can ask is, what if this was like, if sigma of theta prime was 3/2 cosine square theta prime minus half, right? Then you immediately say that, oh, this is nothing but P2 cosine theta prime. Right? So then the only difference is that this will be P2. If this is P2 using orthogonality, this will be 2.
Okay.
If this is 2, I don't replace L equal to 1, I replace L equal to 2.
I would still get rid of that Kronecker.
And still get rid of the Kronecker delta. Now, what you can do now is, what if it is 3/2 cosine square theta prime plus half, right? Right? How do you do then? Exactly. So you subtract and add 1. So you will say 3/2 cosine square theta prime minus half plus 1, right? This is P2 cosine theta prime. What is that? P0 cosine theta prime. And you can immediately see that I can do any function now. I can do this separately, I can do that separately, then linearly combine them. So in principle, given any function, expand it in terms of Legendre polynomials, and then you will get answer in terms of answer in terms of the powers of L. Just for completeness, let's get this done. Get an answer here clearly. This is 1/4 pi epsilon it's good to think of this as an area of a sphere, maybe, maybe, I'm not sure. So that's 4 pi r square times beta, and then there is a r and divided by r square, right? And it is 1 by 3. If it was a quadruple, you get a 5, 7, and so on. You cannot go any further, right? If you want, you can put this out together, that's perfectly fine. I was just interpreting this as charge per unit area. So then this is a charge. So this whole thing has a dimension of charge. The charge times R has a backward moment. The backward moment over. That's just a way of looking at it. But you cannot go further. Right? So that's answer here. But like for example, for practice, this is what I would suggest. Practice, right? 2 sigma of theta prime is equal to 3 by 2 cosine square theta prime minus half. Do sigma of theta prime is equal to 5 by 2 cosine cube of theta prime. Is it plus or minus?
Minus
3 by 2, right? Cosine theta prime. Okay. These are all, so this is P2, this is P3, but then you should also start combining, learn to combine them. So let's say 3 by 2 cosine square theta prime plus half, which is equal to, the hint is that this is 3 times 2 cosine theta prime minus half plus 1. Is that clear? And it should all have dimensions, right? So this should be some beta. Let's say this is beta 1, beta 2, this is beta 3, and something like that. So that should be some gamma. Something. Because just for dimensions, because this charge for unit area and the same thing here. Not gamma, lambda. Okay, and just be aware that this is P2 cosine theta prime plus P0 cosine theta prime. So if you know the answer for this, if you know the answer for this, then you just add them up. For that matter, any linear combination of cosine square theta plus constants you can do now. Any linear combination of that you can quickly construct it, and that's typically how we do. So now you know, in principle, any angular distribution. Give me any angular distribution, and you go rest do this in terms of legendary polynomials. Like angular dependence in theta prime. We haven't done the phi prime. That requires spherical harmonics, which is a small extension of this, but it messes up reasonably well.
How often, like in practice, can you describe like sigma using the phi prime, using cosine or cosine?
Always, any function. It's like a Fourier transform. Any function can be written as a Fourier transform. This is an angular expansion. Like whenever you have a straight line function, like a function going from A to B, then you do Fourier transform. If you're doing on a sphere, angular variables, legendary polynomial. If you look into any astronomical data, like for example, cosmic microwave background, right? That's the data about how much light is coming from everywhere in the sky. That's angular, right? They will expand in theta, right? And they will say, oh, L equal to 1. Your solutions will be in L equal to 1, L equal to 2. How much of L equal to 1? How much of L equal to 2? So how much of dipole moment? How much of quadrupole moment? That's a standard thing to do. Very standard. Like it has nothing to do with electrostatics. The mathematical concept. Oh, yeah. like sine and cosine. Yeah. So very useful for whatever you do. But so my point is, so I'll give one problem out of this, right? Is that reasonable? So you'll repeat this process for one of this. How about this? I will only ask one of this. I won't make it more complicated. One of this. Curtis and Matt, any questions?
None right now.
Okay, good. Yeah.
I'm good.
That's all for today.
Any questions on the test?
4, maximum 5. One on legendary, I told you, right? One on legendary polynomials, one on quadrupole, dipole, one of those. Third is this, and one more. So you pretty much know what other questions are going to be, right? So except for one question, you know. I try to ask 4 questions, but if I find that one question is reasonably easy to do, then. So since this is going to be a little long, right? So maybe I'll stick to 4 questions. So you want to practice a little because this could get a little long if you're not already familiar. Good. Did that answer?
Yeah, I'm like thinking through the homeworks and like what was on each homework.
Where did midterm 1 end, actually?
Does it again?
I was just looking for where midterm 1 ended. Probably right before electrostatics, right?
This homework 6.
This was the latest homework, right?
Okay.
This is the latest homework.
And legendary polynomials were also homework 8.
No, homework. Previous homework was legendary polynomial. Oh no. The previous homework was dipole moment. The current homework is
Current, yeah.
the current, which was due today, is legendary polynomials and this. So the previous homework is dipole moment. And what did we do before that? We did.
There was something similar.
Yeah, it is basically the same. Yeah, I was building up to make this. So first I did the sphere for, at that time seems like, oh, this integral is hard. But this is just P0 actually. That was P0. So concentrate more on 7 and 8, but and let's say electric potential problem, something very simple for an electric. Yeah, electric potential. Remember that we did at infinity. What is the electric potential? And here, what is the electric potential? So electric potential. You remember what I'm saying? Like if you have a triangle, 3 charges, like what is electric potential at the center or anywhere, for example? Something. That I like to ask because that is a training that you got from a previous course. I don't have to blame myself for that. So, good ask questions. I expect that. Okay, so then the questions are kind of fixed. Electric potential, legendary polynomials, electric dipole or quadrupole moment, and this problem, where you find the electric potential due to a arbitrary angular distribution on the z-axis. See, there's a lot of restriction we have put in here, but I wanted to convey the idea. So, but in principle, you can do this for any distribution. But you need spherical harmony, which is very straightforward. You just put an exponential in there. But that's it. Like you know this L for L equal to 3 m runs from -3 to +3, right? Have you seen that in quantum mechanics somewhere?
In chemistry, I think.
Yeah, chemistry actually, azimuthal quantum number, right? That's what you said.
Yeah, I don't remember what they called it. but-
Yeah, so that's the same thing. Yeah, that L is the same thing. That's the reason why this is actually. And again, it's for symmetry, angular dependence. So it's a very natural basis to use, mathematical basis to use. So it's not a surprise that everywhere it's the same L that shows up. So, nice. Okay, I think you.